So, Jai Hind everyone. Today we are here to discuss this topic of electrical measurement and instrumentation, and the topic is current transformer. So, we will be talking about uh, the current transformers, that is a part of instrument transformers uh, in this particular lecture. So, if we specifically talk about the contents of the syllabus, that the current transformers, their phases, and then we will go for their derivations of the CTs for ratio errors and phase angle errors. Basically, current transformers are used to specifically measure the high rating currents. The currents, those are in order of 100 amperes and above. The CTs are used to extend the range of general ammeters, wattmeters kind of instruments, where simply those instruments cannot be applied directly to those high rated currents. So, for that, first those currents needs to be reduced, and then the measurements of those currents needs to be done. CTs are also used to extend the ranges of the wattmeters, as I told you, and energy meters, and the current inputs for the relays, which are used in protection systems. So, the current transformer has two windings, which are called as primary and the secondary winding. The primary winding has fewer number of turns, while the secondary has larger number of turns. It is connected in series with the primary circuit, and the whole circuit current passes through the primary winding, and it is desirable that the voltage drop across the primary winding must be as low as possible. The current transformer has fewer turns of large cross sections, and thus the voltage drop in the primary gets reduced up to a greater extent. So, this is a description of this current transformer. The further description for that could be given as and this is our line current. This is the wave peak to peak voltage which is coming over here, and this is our primary current IP which is coming over here. Here this is the primary winding of this CT N1, and this is the secondary winding NS of this current transformer. The secondary flows through this circuit IS, and this is your primary current IP. This drop should be as minimum as possible in case of this N1, and as it will be minimum, then what will happen? The total current which was supposed to be here in primary circuit will be exactly replicating the current in the secondary circuit. So, primary winding is generally done of thick wires so as to make its impedance as small as possible. So, because of that, least drop is available in the primary winding. Now, secondary winding has more number of turns compared to the primary winding. It is connected with the ampere meter, energy meter, watt meter, or wherever the load is connected. The transducer and the protection relay, the secondary winding of the CT must be connected with the low impedance meters to keep the magnetic flux in the core up to this rated flux capacity. Flux in the core above the rated capacity causes the saturation of the magnetic field, and which leads to complete failure of the current transformer. So, CT current secondary must not be left open. This is the main reason, and it is a very important discussion to be held, that why the secondary of a current transformer is never left open, secondary side. So, the CT secondary must not be left open. Because of this condition, the flux in the core increases manifolds, and it causes the CT core saturation. The terminals P1 and P2 over here shows the primary winding of the CT, and the terminal S1 and S2 shows the secondary winding of the CT. The CT ratio 2000 by 1 means there will be 2000 turns in primary, 2000 turns in secondary and 1 turn in primary through the CT is 2000 ampere. So, that there is a ratio, transformation ratio, which is given as IS by IP equals to N1 by NS or NP by NS. So, this is how the primary current goes 2000 ampere in this case, while the secondary current goes to about 1 time of this number of turns. So, this is the equivalent circuit diagram of a current transformer. The current transformer's equivalent circuit diagram basically depicts the primary winding, secondary winding reactances and the load reactances and resistances. So, this is primary winding Rp and XP as resistance and reactance. This is core loss components of currents IE and IM. This is magnetizing component of the current RE and XM, and this is the no load current, that is I naught. This I naught basically tells about the situation where counterbalancing needs to be done. So, primary current is dependent upon the load current of the main circuit and it is not dependent upon the secondary side of the current of the circuit. So, as far as concerned with the relation between the primary and the secondary is IS by IP equals to, this is given as N1 by N2. N1 is the primary turns and N2 is the secondary number of turns. So, this is the relation that is holding as a transformation ratio. So, here we should be specifically concerned about the secondary resistance, reactance, this is load resistance and reactance, this is induced EMF, secondary side induced voltage, primary voltage, this is the linked flux. So, these are few specific terms which are related to the secondaries. Let me go in details that what these things are, although I have explained all those components over here, especially RC and XM. RC is responsible for the core loss component and XM is the magnetization reactance of the CT. The other CT parameters are given in the following slides. Those slides are containing the details about that what specific factor that we are talking about. So, N represents the turn ratio, RS is secondary winding resistance, XS is secondary winding reactance, RE is the burden connected to the secondary, XC is the burden reactance connected to secondary side, EP is induced EMF in the CT primary, ES is induced EMF in CT secondary, NP is primary number of turns, NS is secondary number of turns, IP is CT primary current, IS is CT secondary current, IM is the CT magnetizing current and I naught is CT excitation current, or we sometimes even call it as no load current. Phi is flux in the CT core and theta is the phase angle of the current transformer. So, these are few terms which will be very important to understand while discussing the case of CT. So, if we want to talk about the description and the derivations of CT, we must understand the primary phasor of the CT first. So, the primary phasor of the CT basically comprises very much similar, it is very much similar to the power transformer. The same phasor has been drawn over here. As you can see, this is a flux which has been taken as a base phasor. There are two components of the current, basically one is the magnetizing component of the current and one is the core loss component of the current. This particular two components results IE and IM is our primary current IP, resultant of these two. When we draw upon the secondary current is IS, this is the secondary terminal voltage Vs, and if we want to implement the circuit basically comprises this one. So, this is the terminal voltage Vs. If we will implement the EMF equation over here, then this will come to as this Vs plus ISRS plus ISXS. As a resultant of that, we will come to have ES over here. So, if we wish to draw this IS in reference to primary, so it will be drawn in phase opposition to the primary. It is N times IS because it is been referred to primary side, and this angle with the Vp will be delta. This angle between Ip and the secondary induced current will be the phase angular, that is theta, and the angle between Im and I naught will be the alpha. So, these three angles are very important to understand, because delta is what? This is the angle between the secondary voltage and the secondary current, and this is reflected back over here because it has been drawn back, and this is the delta angle. The theta is the angle between the primary current and the secondary current. So, these two angles will play major role while in case of describing the relationship between the phase angle and actual ratio errors. So, the equivalent circuit for the current transformer is similar to a power transformer. The current transformer has two types of errors, basically ratio error and phase angle errors. So, as I have described, this theta and ratio error we will talk about now. From the phasor diagram of the CT, the ratio error and phase angle errors could be calculated here. This is the further description, or you can say a small portion of that phasor diagram has been taken to describe further. This further description is about the refer to primary descriptions. So, refer to primary descriptions, we do have base phasor as phi, Im is there, IE is there, those two are perpendicular to each other. The resultant of these two is Ip, which has been drawn, and this secondary current which is referred to primary side is depicted as N times Is. So, if we extend this well to this particular point B here, and we make a right angle to this particular point. So, we can find this angle if we represent this as O, this is O, not theta, you can correct it. This OBC triangle that we want to understand, that OBC representation basically tells us about this description, that if this angle was theta, this angle was delta, then this angle will become 90 minus alpha minus delta, and this angle is alpha. So, this angle will be 90 minus alpha minus delta. So, CT transformation ratio is calculated as follows. We need to calculate the primary current as per the definition and then divided by the secondary current. So, that is what the transformation ratio is, that is R Ip by Is. This is our transformation ratio of the secondary. So, if we want to calculate this, then we need to find out the components of the phasors along with the direction. So, if we find from the phasor primary current is Ip, if we want to find out Ip over here in triangle O, B and C, how we will calculate it? The CT primary current Ip can be given as I naught square, that is, this is the projection of this in this direction, plus N times Is, the projection of this here, and NIS square, plus 2 I naught NIS cos 90 minus alpha minus delta. So, that will be your Ip, and the CT ratio is equal to Ip by Is as given also. So, R will become under root I naught square plus NIS square plus 2 I naught NIS in alpha plus delta. We will neglect over here a specific component, that is this N I naught 2 I naught NIS cos 90 minus alpha plus alpha minus delta will be sin alpha plus delta as per the description. Further elaborating about here, the magnetizing current is I naught is a very small fraction. It is a very small fraction, and when it is compared to the primary current Ip, because Ip is of very high order, large order, and the expression further could be simplified as I naught square plus NIS square 2 I naught NIS sin alpha plus delta upon Is. So, if we want to implement over here NIS square plus I naught sine alpha plus delta square plus 2 I naught NIS sine alpha plus delta over IS. So, here we can write it as the whole square of NIS plus I naught sine alpha plus delta. So, here the expression after solving comes NIS plus I naught sine alpha plus delta upon IS, and the expression further becomes, when we divide it over here, N plus I naught sine alpha plus delta upon IS. So, this is the final expression for transformation ratio. So, from our expression we deduce this, that the transformation ratio is not equal to the turn ratio, that is R not equal to the N, where R is this one and N was simple N2 by N1. So, this was the basic turn ratio N, capital N. So, this is not equal to R. R is something which is coming as N plus I naught by IS sine alpha plus delta. So, the transformation ratio and turn ratio will be equal only and only when this delta term and alpha term both will become 0. When these will go 0, this condition can be achieved only if the core loss component is equal to 0 and the burden is completely resistive. That is the load that we have connected in the secondary side, that if that is purely resistive, then this could be happen. This R could be equal to the turn ratio, otherwise it will not happen. This is an ideal condition, however, the condition is practically impossible to achieve. Now, let us talk about the phase angle error of the transformation, particular current transformer. If we want to calculate the phase angle error over here, so further going back to that phasor that we have calculated this angle 90 minus alpha plus minus delta, this is delta, this is theta, this is alpha. So, if we want to calculate tan theta over here, tan theta will be OB BC by OB, that is BC, this perpendicular, and this is your base. So, BC by OB. So, if we calculate I naught sine 90 minus alpha minus delta upon OA, that is this much, and plus AB, OA plus AB. So, if we put these values and solve further, so if the theta becomes very small, then we consider tan theta equals to theta, then theta becomes I naught cos alpha plus delta upon NIS sin plus I naught sin alpha plus delta, as I naught is also very small as compared to IP. So, I naught sin alpha plus delta will be very, very lesser than this NIS. So, hence I naught sin plus I naught sin alpha plus delta can be neglected further. So, theta comes to as this one. So, further elaborating this, if we elaborate further and open this expression for alpha plus delta, then the expression coming to be as I naught cos alpha cos delta minus I naught sin alpha sin delta. From the phasor we can find out this I naught cos alpha is equal to Im and I naught sin alpha equals to I. So, further this Im cos delta minus I sin delta Im cos delta minus I sin delta upon NIS is in radians. If we want to convert that into degrees, you need to multiply it with 180 by pi. Though further some parameters related to CTs are this CT ratio error. Ratio error is defined as the per unit deviation in the transformation ratio from its nominal ratio. The ratio error is expressed in percentage. The ratio error equals to nominal ratio minus transformation ratio upon the transformation ratio multiplied by the 100. So, that will give the percentage ratio error. Since the burden of the CT is generally resistive, therefore, the power factor of the burden is considered to be unity, which is a impossible case, because most of the burdens are having somewhat components of inductance, and hence at that moment the delta becomes 0. When it becomes purely resistive, which is a hypothetical situation, in that cases the delta becomes 0. So, if we put the expression over here for the R equals to n plus sine n plus I naught sine alpha plus delta upon Is, where delta becomes 0 for resistive burden. So, it becomes n plus I naught sine alpha upon Is, and here I naught sine alpha is IE. So, R becomes n plus IE by Is. So, this is ratio error that we can calculate from here, from this formula. Now, the phase angle of current transformer, when we have calculated, the phase angle is actually nothing but the difference between, that is theta, that is angular or displacement between the primary current and the secondary current. For as far as concerned with the expectation of the user, it should be minimum. Phase angle should be minimum. So, the phase angle between primary and secondary of the current must be 180 degree, or it should be. The primary and secondary current must be out of phase. The deviation in the phase angle of the primary and secondary current is called the phase angle errors. The phase angle between primary and secondary current of CT is denoted by theta. Since the burden of CT is generally resistive, therefore, the power factor of the burden is unity, and hence the delta becomes 0 in this case when completely resistive load. The phase angle of the CT is given by following expression: 180 by pi Im cos delta minus I sin delta upon NIS. So, here if we calculate Im cos 0, we put delta as 0. So, only this cos 0 will become 1 and this will go 0. So, the only expression that is remaining over here is Im by NIS in radians, or 180 by pi Im by NIS in degrees. Since the burden of CT is generally resistive, power factor of the burden is, again it is emphasized that this particular thing is very important to understand. So, here two specific things that we need to point out here, that the phase angle error is due to basically the magnetizing component of the current, that is Im is playing a major vital role over here, and these errors are introduced due to Im itself and IE itself. Those two particular factors are responsible for introducing these errors in the current transformers. Im and IC needs to be decreased to reduce the phase angle errors, and these two discussions that I have already told you about is regarding this, the Im and IC causing these errors to be produced further. Another important question that we left to discuss over here is about that in between we have talked about this, the non opening of the secondaries. While operating, the secondaries of the circuit of CT should not be left open. The reason behind that is that the basic reason, the basic dependency of primary current is dependent upon the load current itself of main circuit and not on the secondary side of the current. So, as the current in the main circuit changes, the IP, then IS will change accordingly also. IS is depending upon IP. If IS is left to be 0, that is open circuited, so under that condition what will happen? There will be no counterbalancing component for the primary MMF. As the primary MMF will not be balanced, it will go into the saturation and will increase the magnetizing current very highly, and thus this could burn out the current transformers descriptions or coilings. So, this was about the CT descriptions. In further we will talk about PTs or some different topics that will come all together. So, thank you and Jai Hind.